Hey everyone, it's Vici here. Today I wanted to talk about a book that I've recently read called Gödel, Escher, Bach, and Eternal Golden Braid by Douglas Hofstadter. So it's quite an interesting book because Kurt Gödel, was a mathematician in the early 1930s who discovered some incompleteness in formal systems in mathematics. And then MC Escher was an artist who produced mathematical type art in the mid 1900s. And then we have Johann Sebastian Bach, the musician in the 1700s, who was a classic music composer. So I found the book very interesting because it goes through all these different areas and actually creates some genuine connections between them in rather unexpected ways. So what this video is going to be kind of a summary, but also kind of just things that I find cool about the book. So it's half a summary and half just my interpretation of it and what I thought was interesting. So I hope you enjoy. The first thing we'll start off is with this sentence is false. What is this sentence saying? If the sentence is true, then it is saying the sentence is false. But if the sentence is false, then it's saying that the sentence is true, because if saying the sentence is false is a false statement, then the opposite must be true, so it's a true statement. So this is a paradox. But it's easy to dismiss this paradox because this is the problem, the word this. So this doesn't actually explicitly contain the whole sentence. For us to understand that the word this refers to the sentence requires a lot of cognitive machinery in our minds to do that interpretation, because there are some situations where this sentence might actually refer to a different sentence. So our brains have to figure out, based on context, whether this sentence refers to specifically its own sentence, whether it's being self-referential, or whether this sentence refers to perhaps a previous sentence or the following sentence. For example, I might put in quotes, I have a big blue hat, end quote. And after that I might say, this sentence says something about my clothing. In that case, this sentence actually refers to the previous sentence. So the sentence, this sentence is false, is not quite self-referential. It requires some sort of human context, human understanding to make it self-referential. It's not inherently self-referential. So that's just a starting point. So we'll continue on later with self-reference and some of the other ways that self-reference can occur. But for now, we'll move over to the ideas of isomorphism, analogy, and mapping. Hofstadter uses the word isomorphism a little bit more loosely than it is normally used in mathematics. So in the book, he just means an isomorphism is when two things correspond to each other, or two things map onto each other one-to-one. For example, two chairs are isomorphic in a way. They both have the function of you can sit on them, they both have legs, they both have a back. Perhaps some of the details are a little bit different, but there are certain features about both, or functions, that you can map onto each other one-to-one. Even if one of the chairs only had 3 legs, there would still be an isomorphism because the idea of legs can be mapped one-to-one from each of the chairs. But in this case, both of the chairs have 4 legs, so there is an even lower level isomorphism of literally each leg has a one-to-one correspondence to a leg on the other chair. Another example of an isomorphism is, say, a computer and a human. There is what we could call a high-level isomorphism in that both the human and the computer are calculating machines of some kind. They can do some kind of manipulation of data. However, at the lower level, the isomorphism breaks down. The way that computers actually work and the hardware and the software is extremely different to the way that human minds work. So at a lower level, the isomorphism doesn't hold, or the mapping doesn't hold, but at a higher level, it does. Another isomorphism is, for example, the vice president is like the spare tire of the government. So in this case, while a spare tire doesn't literally look like a vice president, they both have the functional purpose of being backups to the main thing. So in that sense, at that level, they are isomorphic. So in general, things that are more different would have higher level isomorphisms, while things that are more the same have lower level isomorphisms. So two chairs have an extremely low level isomorphism. a human and a computer have a higher level isomorphism, and a spare tire and a vice president would also have a pretty high level isomorphism. The exact point, or exactly how high a level, isn't really the point, but the idea is that isomorphisms are one-to-one mapping between things. And that's also related to analogies. So an analogy is when you have another situation which is in some way mappable onto another situation. We understand one situation, or perhaps we're trying to explain to someone one situation, and we create analogies so that the person we're explaining to can understand what we're saying, and the analogy has some important mapping to the actual situation. And because perhaps that other person understands the situation of the analogy well, they can map their understanding of that analogy onto the particular situation that you're trying to explain, because there is that one-to-one mapping or isomorphism between the analogy and the thing that you're trying to explain. This idea of isomorphism, mapping, and analogy is something important to keep in mind as we move forward with the rest of the video. Another idea to talk about is levels of abstraction. So we can move up or down levels of abstraction. When we move up levels of abstraction, we might chunk or put lower levels together into larger single units. Or when we go down levels of abstraction, we reach lower and lower levels. So for example, a computer system is a perfect example of abstraction. At the absolute lowest level, well, depending on how low you want to go, you have the logic gates. At the lower level, there is the actual physics of how the logic gates work, but I don't know too much about that in detail, so I won't explain it. However, then we have the logic gates, and that's a pretty low level. And then you put a few gates together in a certain way, and you can create, say, for example, an ALU, or an arithmetic logic unit, and that can do calculations. So you have this higher level, you have this unit, which you put in numbers, and it adds them together, perhaps, and it returns the answer. So that's a higher level than the logic gates. You don't actually need to understand the logic gates to use the ALU. And then you can keep on moving up higher and higher levels, all the way to you can use a computer and you can do things with the computer without necessarily knowing what's going on underneath. Even programmers, when you write a program, you don't actually have to know what's happening under the hood. It might be helpful to know what's happening under the hood, but you don't have to know what's happening under the hood. You could, in theory, teach someone to program reasonably well without teaching them binary, which is what computers are in. So someone could write a program, they could even make a game, a really complicated game, but not know what binary is. It would really help to know binary because there are some quirks and things in languages that involve using binary, but they don't need to know binary. So that's the idea of moving up or down levels. Another example of moving up or down levels is, say, human psychology. At the really low level, we have the neurons. That's just neurons which get fired or not fired. And then you move up a few levels, and there's a lot of stuff we don't understand about the brain. These are what you call the intermediary levels. But then at the high level in the brain, we have the symbols, the stuff that you can consciously think about. You can think ideas, you can manipulate ideas. This is a much higher level than the neurons right down at the bottom. Or of course, if you want to go lower, then it is of course the atoms below the neurons that are even lower level than the neurons themselves. And then moving to a higher level, we have people, and then you can have societies or anthropology or cultures, and that's a higher level than the psychology. And you might even go to the highest level of all, if there is a highest level, and politics. You can say politics, or in general, the organization of society is the highest level in the human context that we would think about. Perhaps there are higher levels to think about reality, but societies aren't sufficiently complicated for that to make too much sense right now. The highest level that it makes sense for us to think about is politics and how society is organized and such. One of the interesting things that he discusses is the application of Cantor diagonalisation to computer programs, which is essentially a variant on the halting problem. So I'll explain the halting problem first, and then I'll explain Cantor diagonalisation, and then how combining those two can create some sort of alternate halting problem. The halting problem essentially is you have a program, and the question is, if you put this program with a certain input into a potential program H will tell you, will this program halt or will it not? Because some programs will go on forever. Perhaps there's a while loop and the condition that makes it break out of the while loop never gets satisfied. So it just loops and loops and loops forever. Alternatively, maybe it does get satisfied and the program halts. So here we have this hypothetical program H, and let's assume that this program H can determine whether or not a program and an input will halt or not. So it takes in a program, it takes in an input, and then it determines, will this program halt on this input? Now what we do, let's create a new program. Let's have this program H, and let's say that for a given input, which is a program and an input, let's say if the H determines that this halts, then an infinite loop starts. So if it halts, if it decides that this halts, it goes into an infinite loop. And then if the program H determines that these loop, then it goes, and then it just halts. Now what we'll do is we'll put all of this in some bigger program. Let's call it H+. So all H+ program is, it's the same as H, but if it determines that the input halts, then it'll loop. If it determines that the input loops, then it'll halt. Now what we do is we set up H such that it takes in some code, and it uses that code both as the program and the input. So let's say the code is 11001011. That's not a very interesting program, but just imagine that that was a lot longer than it was. So what H will do is it'll read this as a program, and then it'll also take this as the input to that program. So that's what H does in this particular scenario. So now the question is, H+, let's say we get source code for H+, and let's just call it source X. This is the source code for H+. What happens when you feed source X into itself? So here we are feeding source X into H. Now what will H do? H thinks, okay, we have X, and that X is a program. We're going to feed X as data into itself. Let's say that H determines that this halts. Then this will start looping. Alternatively, let's say that H determines that this loops. Then it will halt. It doesn't seem like a problem, except for the fact that what H is simulating is in fact H+. So if H determines that X halts, then H+ will loop. If H determines that X loops, H+ will halt. But as it happens, X is H+. So does the program loop or halt? It's a paradox. If it halts, then it must loop. If it loops, then it must halt. So the only conclusion that we can take from this is that our assumption that H is possible is faulty. So the idea is this particular thought experiment makes us come to the conclusion that a program like H, which can determine whether or not another program and input will halt or not, cannot be possible. So H does not exist. So now let's talk about Cantor diagonalisation. So the question is, how many numbers are there? These are the natural numbers, so it seems like there's an infinity of them. Okay, so what about fractions? How many fractions are there? Well, if we create a certain special way to write fractions, if we write out all the fractions like this, so we have an infinite thing going this here onto infinity, we have an thing here going on to infinity, and so here we will come across every single possible fraction you can write, because we've got every single possible natural number over every other possible natural number. So now let's start here. We start here. Now let's move 1 here, 1 over 2. Okay, now let's move here, 2 over 1. Now let's move down here. So let's go through snaking our way across like that. and that goes there. So we snake our way, and basically, of course, sometimes it'll double up because 2 over 2 is the same as 1 over 2, so we can just cross over the ones that have already come across. But the idea is we can map every single fraction onto the real number line. There is a one-to-one correspondence between the number of fractions and the number of natural numbers. Intuitively, this might not make much sense. It obviously seems like there are more fractions than there are whole numbers, but they're actually the same number because they're both infinities are the same size. So now comes the question, what about irrational numbers? So what about things like the square root of 2? Is there some way of mapping every single irrational number onto the real number line, onto the natural number line? And by the way, an irrational number is simply a number that cannot be expressed as a fraction. So square root of 2 cannot be expressed as a fraction. You can approximate it with fractions, but you can't actually calculate it exactly with a fraction. There is no no natural number such that a over b is equal to the square root of 2. This is not a thing. So the question is there some sort of mapping between irrational numbers and natural numbers? Because we know there is a mapping between all fractions or all rational numbers and all natural numbers, but we don't know about irrational numbers. So the idea is this is actually impossible, and this is the proof. Imagine you manage to create a list of every single number between 0 and 1. So let's go 1, 2, 3, 4. So let's have the first number, 0 point something. So here we have the list of every single possible number between 0 and 1, and let's assume that we have mapped each one onto a natural number. Let's assume this. Now let's create a new number, 0 point. So the first number here is 5. Let's add 1 to it, 6. This is 2. Let's add 1 to it, 3. Next diagonal 1, let's add 1 to it, 2. Next diagonal 2, let's add 1 to it, 3, and let's so on. Now let's say we go and do this and it's infinitely long. Now this number that we've just created cannot be anywhere on this infinitely long list because we have constructed it by going through this infinitely long list and adding 1 to every single digit. This is Cantor diagonalization. Cantor was the mathematician who discovered this or created this. And this diagonalizing. So you take the diagonal and you add 1 to every single one of those digits to create a new number that cannot be on your list. What this means is that there are more than one size of infinity. So the numbers 0, 1, 2, so on, those are really the natural numbers, and then all the fractions, so 1 over 1, and in the method that we did before, 1 over 3, whatever the sequence was, these two are one size of infinity. Whereas the size of irrational numbers, so that is any number that can be expressed as a decimal, is an infinity larger than these two. So you cannot map these one-to-one here. So this key point of Cantor diagonalization, what we're going to do is we're going to create an analogy between this particular Cantor diagonalization with numbers and with programs. So that's what we're about to do. Let's say you wrote out a list of every single possible program. So we'll start off with all of the programs that are 1 character long. Let's assume there are 50 characters. How many possible programs are there with 1 character? Well, there's 50. How many possible programs are there with 2? Well, 50 times 50, 50 squared. How many possible programs are there with 3 characters? 50 cubed. So we can order this 50 alphabetically. So we have a way to order this. This 50 squared, we can, again, order this alphabetically. If we create an alphabetical list for all the characters, let's say A to Z, and then Z, and then 0 to 9, and then bracket, square bracket, asterisk, and so on, all 50 characters, let's just say. It's alphabetically ordered. What this means is that every single program that can be written with these 50 characters can be mapped onto the natural number line. So there is a one-to-one correspondence between the number of natural numbers and the number of programs that can be written. Okay, great. Now, what do we do with this? Well, the first step is to remove all the programs that are nonsense, programs that don't even run, the bad syntax. So we'll cross out all those programs and then fill up all the gaps, and we still have a one-to-one correspondence. Let's say we had 1, 2, 3, 4, 5. This is program A, this is program B, C, D, E. Let's say it turns out that C has bad syntax, we just cross that one out. Let's say it turns out A also has bad syntax, we cross that one out. So now we have a new correspondence one-to-one, B, D, E, F, G, let's say, and F and G were here and here. So it's not a problem. We can easily cross out all the ones that have bad syntax. Now let's exclude every program that does not take an integer as input. Now let's assume we have a program H, and let's say that this H can determine whether or not a program is going to halt, and if it does, it'll exclude the ones that don't return an integer. So when you put in any one of these programs from this list into H, it'll either say loops forever, or it'll says halts and doesn't return integer, or halts and returns integer. Now what we can do is we can exclude every single program that loops and that halts and doesn't return an integer. So all we're left with is a list of programs, 1, 2, 3, 4, so on, and this will be presumably an infinite list. Well, it will be an infinite list actually, because you can always create another program that halts and returns an integer, but just by adding +1 to whatever the output is. So there is in fact an infinite number of these programs. But let's say we've got left with B, H, K, so on. So here we have this infinite list of programs, all of which halts and returns an integer. Now comes the Cantor diagonalisation. Let's say we have a new program. Let's call this program B for big, because it's probably going to be a rather big program. What this program B is going to do is, let's say it takes in an integer. So this program takes in integers. Let's say it takes in the number 125. What it's going to do is it's going to do, all of these processes are well defined. So let's assume that it goes through all these processes and it finds the 125th program, or it finds the program that corresponds with, let's say JJG is the program. It finds the program that corresponds with 125, and then it puts 125 into that program and sees what comes out. Let's say GGJ spits out 382. Let's say that's what it spits out, because this is the list of every single program that halts and returns an integer. So let's say that JJG, GGJ, BJJ returns 382. So what this program B is going to do, it's going to look at that program, it's going to find it, it's going to find what it output, and then what it itself do is it will output 383. So it'll add 1 to this output. Let's say you put into this program B 200. What it'll go and look at the 200th program. Let's say this one is actually BJJ, and this returns 1131. What it'll do is it'll put 200, it'll pass 200 into BJJ, which is the 200th program. It'll find it has 1131, and it'll return 1132. So this program, now let's think about this program B. This program B, it halts. It's well defined for every single input. Every single step of this process was well defined. So it halts and returns an integer. But by definition, B cannot be somewhere on this list. Because if B was somewhere on this list, and let's say it was at position 4000, let's just say B was at position 4000, then, and let's say it returns 200, well then B would look at the 4000th program, B, find that outputs 200. Oh no, that's confusing. Let's say it outputs 13. Then it'll output 14. If it puts 4000 into the 4000th program, which as it turns out is itself, it put 14. But it can't output both 13 and 14 at the same time, which means B cannot be on this list. Which means here we've come up with a program which it halts and returns an integer, so it must be on this list. But we've just used a method very similar to Cantor diagonalisation. We've literally added 1 to the output. So it's almost exactly the same thing, except applied to programs rather than irrational numbers between 0 and 1. So what's the problem? There is some problem somewhere, because every single step of the way it was great, and we've come with a contradiction. Well, the problem comes with assuming that this program H is possible. We assumed that it was possible to determine whether or not every one of these infinite programs could halt or loop, because we know that this list is complete. We know for a fact that every single program that can be written must be on this list, because we're literally going through brute forcing every single program. So this is just brute force. Any program of finite length will be on this list, and this program is going to be of finite length because it's well defined. It doesn't need to be infinitely long, even though there are infinitely long here. It doesn't actually need to be infinitely long itself, because the construction of these programs is well defined. We've just gone through and alphabetically ordered go through everything. So all you need to program it be is the instruction as to how to make this list. So we know that this list contains every single program that halts and returns an integer, but the problem is the assumption H. So this H can't exist. So this is an alternate way to see the halting problem. It's essentially the same thing as the halting problem, except it's explained through Cantor diagonalisation. So the idea is that there are two conclusions. Either H is not possible, or there must be some kind of programming language that is more powerful than this programming language. I don't know the details of the proof for why that's not the case, but it is the case. I don't know why. I'll have to perhaps provide a link to the proof and further details in the description, but that is not possible to have a programming language more powerful than the most powerful programming languages that we have today. A Turing-complete programming language, such as any regular programming language you come across, like Python or Java or C or whatever, is sufficiently powerful to create any program. We know this. I don't know this, but it is known. And now we come to formal systems. So Gödel, Escher, Bach goes through quite a lot with formal systems. He takes a long time to explain it, but he explains it very thoroughly and very rigorously. And so I'm just going to go through some of the examples he uses to explain formal systems and get a bit of a feel of what goes on and what are the implications of things within formal systems and problems with formal systems. So the first thing is we have the mu problem. So let's say we have M, I, and U, and this is our bag of letters. These are just random symbols, M, I, U. So there are 4 rules and 1 axiom. The first axiom is MI, and let's call this a string. So anything that we produce with these symbols is a string. So I, U, M, I, U, that's a string. We would generally put quotes around it. I'm not going to write quotes around every single one, but that's a string. So as opposed to like 5. 5 is not a string. If we wanted to put it in quotes, it would be a string, but 5 wouldn't be part of this system because 5 is not part of the bag of letters. If we have MIO, that is not a string in this particular formal system, but it is a string in general. So that's the idea of strings. So whenever I write things like MI, what this is a string. So this is what we can call the axiom. This is the starting thing that we assume is true. And then we have 4 rules. So rule 1. If there is an I anywhere, it can be replaced with an IU. So if there's I anywhere in the string, we can replace it with IU. Rule 2. If there is M followed by a string, X represents a string, we can replace it with MXX. Rule 3. If there is an I anywhere in the string, we can replace it with a U. The final rule, if there is a U anywhere in the string, we can replace it with nothing. We can just delete the double U's. So what's going on here? So we have the axiom, MI. Let's apply rule 1. So we apply rule 1, and we get to MIU. Now, this is called a theorem. We're going to call this a theorem because it was derived from the axioms. So we have axioms, in this case just one. We have these rules, And any string that we can reach by applying these rules to the axioms are what we call, by definition, theorems. So MIU is a theorem. Let's see what else we can create. MIU, let's apply rule 2. So we create MIU, IU. So in this case, IU is X, and we're just doubling it. So MIU, IU. We could have also started from the axiom differently. We could have gone rule 2 and created MII. We could have applied rule 2 again and found MII, and then we could apply, say, rule 3, and we could get MIU, because we replace these 3 I's with a U. So this is the axiom, these are the rules. So the question is, find MU. In other words, is MU a theorem? If MU is a theorem, it's derivable from the axioms using the rules. If MU is not a theorem, then it is not derivable from the axiom using the rules. So this is our first introduction to formal systems. What it is, it's some typographical, just some symbols, literally some symbols that we start with, axioms. Then we have rules, which are some mechanistic, mindless ways of choosing how we can and can't manipulate the symbols. So we have the axioms, which are a sequence, which are a set of strings that we assume are true. And then we have the rules. And when we apply rules to the axioms, they produce new strings. And we're going to call these new strings, by definition, theorems. So in this particular case, the question is MU a theorem? Now, I'm not going to provide the answer to this. I'm going to leave that as an exercise to you, the viewer. So these are the rules. That is the axiom. Is MU a theorem? You can, of course, search up the answer on the internet. But yeah, that's an interesting problem to work on. I highly recommend going to work on it for at least 10-15 minutes. Work on it until either you've found the theorem or you've proved why there is no theorem. And so that should be an interesting exercise. So the next formal system that we are introduced to is called the PQ system. So what are the axioms? X, P, dash, Q, X, dash. This is an axiom as long as X is equal to some number of hyphens. So for example, dash P, Q, dash P, dash Q, dash X is an axiom. Dash dash P dash Q dash 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 is also an axiom. So these are strings, and they're also axioms. And there's only one rule. You can turn X, P, Y, Q, Z into X, P, Y, dash, Q, Z, dash. So in this case, X, Y, and Z refers to some number of hyphens in the same way as X here refers to some number of hyphens. So if you have dash, dash, P, dash, dash, Q, dash, dash. If this was a theorem, then you could turn it into dash, dash, P, dash, 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 Q, dash, dash, dash. So if this was a theorem, then this would also be a theorem. So that's a rule. So let's see what we can derive. So, okay, let's start off with just dash, P, dash, Q, dash, dash. Okay, let's use this rule. Let's see, we got dash, P, Q, dash, dash, P, Q, dash, dash, dash. Okay, let's use it again. That rule again. Dash, 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 Q, dash, 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 dash. Okay, so we can see that this increased by 1 and this increased by 1. Okay, let's start with a different axiom. Let's start with 3 hyphens, dash, Q, dash, 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 dash. Okay, let's apply the rule to it. Dash, 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 P, dash, dash, Q, dash, 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 dash. And let's apply the rule again. Dash, 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 P, dash, 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 Q, dash, 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 dash. All right, so these are all theorems. We've started with axioms. So this was an axiom. This is an axiom. We've applied these rules. We've gone to here. We've gone to here. So here's a question for the viewer. Before you continue watching the video, what is going on here? So let's try and figure out what this might represent. This is a good exercise to do. When you've figured it out, you'll realize how obvious it is, but if not, you can continue watching the video and that's fine. Although it is a good exercise to try and figure out what's going on yourself. And I'll give you a few seconds to pause the video and go off and do that if you want. What happens if we interpret the number of dashes as a number, we interpret the P as plus and the Q as equals? Well, what do these statements all turn into? This statement, 1 plus 1 equals 2. 1 plus 2 equals 3. 1 plus 3 equals 4. 3 plus 1 equals 4. 3 plus 2 equals 5. 3 plus 3 equals 6. So you can see that under a certain kind of interpretation, we're getting meaningful results. So the idea is, hopefully, every single theorem that we derive under interpretation comes out with a true result. We're going to say something like 3 plus 3 equals 6. That's a true result, right? So let's assume that we had all the axioms and then we applied all the rules to all the axioms in as many ways as we wanted. We would really hope that under interpretation, every single one of those theorems comes out as a true statement about addition in mathematics. So now if we were to ask the question, is a certain string derivable from the axioms, or is a certain string a theorem? Let's say I write dash p, p, q, q, dash, dash. Well, if we look at the axioms and we look at the rules, it's pretty obvious that it doesn't matter what you do, you can't derive this particular string from the axioms using the rules, because none of the axioms have more than one p, and none of the rules involve increasing the number of p's. So we know just by looking at this that this is not an axiom or a rule. But a key thing here is that we only know this because we are able to think outside the system. Imagine if you were a mindless computer. Actually, it's not right to say mindless computer. Let's say you were mindless, because it's part of the book discusses the relationship between computers and minds. So for me to say mindless computer is not the right thing to say, because it has all sorts of connotations which aren't necessarily what I want to create. However, let's say you were mindless. You would start off with every single axiom, and you would apply each rule to each axiom, and you would check if the resulting string is the same as this string. But what would happen? You would just go on. You would try. Let's say you start off with this axiom. Let's say we have the list of every axiom here infinitely, and then going across we have every single applying the rule. So here we have the axiom where x is just 1 hyphen, we apply the rule infinite times. X is 2 hyphens, apply the rule infinite times. X is 3 hyphens, apply the rule infinite times. And let's say we use the same snaking across method. And let's say this particular, let's say you as a mindless being does this snaking thing, and every single one you come across you check. Is it the same as this one? No, move on. You will never do it. You'll just keep going forever and ever. You will never be able to know that this is not part of this. But by inspection, because we're able to move out of the system, we're able to see just by inspection, by looking at it, that this string is impossible to reach from the axioms using the rules, because none of the axioms or rules involve having more than one p. So having more than one p means we automatically know that this is not a theorem. So now we're building up closer and closer to what I think is kind of or close to the crux of the book, which is Gödel's incompleteness theorem. So let's go through a few ideas first. So let's create the distinction between use and mention. So if I say apple has 5 letters, I ate an apple. In this case, apple is being mentioned. In this case, apple is being used. So by having it in quotes, it's a string, it's being mentioned. So for example, if you have 5 plus 5 equals 10, in this case, 5 and 5 are being used. But if you put that in quotes, 5 plus 5, this is just a string. It's just the character 5, a space character, the plus character, another space character, the 5 character. So this is being used, and this is being mentioned. So now let's talk about quines. So quines are quite interesting things. Consider this sentence. Yields a sentence when preceded by itself in quotations, yields a sentence when preceded by itself in quotations. So this is one sentence. The sentence starts here, and then it goes across, and it ends here. So this is an example of being used, and this is being mentioned. So what's happening here is that we have something which has meaning here, and then something which is a string here, but the thing that has meaning and string is the same thing. So it doesn't always work. If you have tree, then it doesn't make sense. If you have trees are green, trees are green, that doesn't make sense. This doesn't in fact work. This, however, does work. Is a sentence. Well, actually, does this work? Well, no, this is actually false. So this doesn't make sense. This doesn't make sense at all. But this one is actually false. So this one is true. This one is actually false. Because is a sentence is not a sentence. Whereas if we said is not a sentence, is not a sentence, well, this is actually true. Because is not a sentence, that in fact, that's not a sentence, is not a sentence. That has no subject. So it is true that this is not a sentence, so is not a sentence. But the thing is, this is self-referential. This is semi-self-referential. So the thing that is doing the referencing looks like what is being referenced, but it is not the same thing. So what if you wanted to write a sentence that entirely references itself? It doesn't just reference a copy of itself, it references itself. Well, we started with that. This sentence is false. Except the problem with this one is that this requires cognitive machinery. So what if we wanted to write the whole sentence within the this? We would say, this sentence is false. It is false? Well, no, this is not a paradox, because this might be true. This might be false. The sentence might be true and this might be false, so that this is not really a paradox, because of course this sentence is false as a sentence when it's being used as a paradox, but when it becomes mentioned, or when it's just as a string, this sentence doesn't make sense actually. So what if we wanted to write a properly self-referencing sentence? Well, we'd have to do something like this. The sentence has to contain itself. So let's do this. The sentence, okay, it has to contain itself. Okay, well, it has to contain this as well. So, and then we'd have to do an infinite number of iterations, and then is false, is false, is false. That's an entirely self-containing sentence, where this is infinitely long. Because if you say here, this sentence, the sentence is false, if you have a look at this part, it is exactly the same as this, because there's infinitely long. Problem with this sentence is that it's infinitely long. So this is fully self-referential, but it's infinitely long. So we have a bit of a problem. So what Gödel did is he managed to find a way for numbers to reference themselves properly without infinite regress. So this is how he did it. So let's create the formal system. So in the formal system, there are a couple of symbols, there are a couple of things that mean different things. This means not. This means there exists. A is a free variable. The colon means such that. And this is our interpretation of it, by the way, not what they actually mean. These are just meaningless symbols. These are just our potential interpretations. S means the successor of. Prime is just prime. It's going to be used to have free variables. So you have A prime, prime. They're all just free variables. We could use A, B, C, D, E as free variables, but we're just going to use primes, so just to keep the list finite. Because if you had A, B, C, D, you'd have to create an infinitely long symbol list. Using prime, is just a way to get around that. The same way the successor of is a way to get around having an infinite number of symbols for all of the natural numbers, because S0 would mean 1, SS0 would mean 2, SSS0 would mean 3, and so on. This upside down A means for all, and then there's brackets. I'm not going to write out the brackets, and there's plus, minus, times, and divided by. That's all we really need. And now in this formal system, we're going to have an axiom. Let's say this is an axiom. So it is not the case that there exists an A, so there exists a natural number. And this formal system only talks about natural numbers. So 0, 1, 2, 3, 4. Numbers like 4.5 are not, they're not part of this system. They're not represented in this. So what this is saying is there does not exist an A such that successor of A is 0. In other words, -1 is not, there is no -1. So this is saying we're only talking about natural numbers. And here's another one. For all A, so what this is saying is for every number has a successor. So for all A, so for every single natural number, like 5 or 17 or 381, there exists another natural number such that the other natural number is the successor of, or 1 plus that. So these are two axioms. There are some more axioms, but that's not really the point. There are also some rules that we have for manipulating these axioms, but again, that's not the point. The point is we have some axioms and we have some rules. Much like earlier in the previous systems, there are axioms and then there are rules. And from each of these axioms, we can apply the rules in a variety of ways. Let's say there are 5 axioms. We can apply the rules in a variety of ways to create theorems of the system. So let's say that this theorem is created by applying a certain rule to this axiom. This theorem is created applying a certain rule to these two. This theorem is applied by these 3 axioms. This one is applied by setting a rule from this axiom, and so on. Let's say this is generation 1. And these are just lots of theorems. So they're all strings and they're all theorems. And we're deriving rules from the axioms. So this will look like some sort of complicated tree. So for simplicity, let's just draw it as a simple tree. It's not actually like this, where it branches out neatly like this. It branches in very complicated ways because each theorem could be derived from multiple axioms or involve multiple rules being applied in different ways. But the idea is every single string on this tree is a theorem. So the question is, if we have a random string S, is it going to be on the tree or not? If it's very close to the axioms, we might be able to try a little bit experiment. But the question is there any rigorous way to determine if S, the string S, is somewhere on this tree? In other words, is the string S derivable from the axioms? Is it a theorem? Another thing with this formal system is that we would sincerely hope that every string that we derive, every theorem under this interpretation comes out to a true statement. So let's say we start with these axioms and we apply these rules and we get some sort of theorem that says SS0 is equal to SSS0. That's a string. Let's assume let's say that this is a string that we somehow derive from the axioms. This is bad because this under interpretation means 2, this symbol under interpretation means equals, and this symbol under interpretation means 3. And this is obviously false. So it would be a real problem if we came up with strings or we derived strings that corresponded to false statements, because all of this string manipulation that happens is just mindless manipulation of symbols. These quote-unquote axioms, they're just random symbols. These rules are just random ways that we have of manipulating those symbols. It's only under interpretation that they become meaningful. So what we would hope is 2 things. One, what I said, that every single string that we derive or every theorem has an interpretation in mathematics that is true. We would also hope that everything that is true in mathematics is derivable within the system. So let's say I come up with some true statement like 5 times 5 is equal to 25. We would hope that SSSSS0 times SSSSS0 equals S, 25 of them. We would hope that this is derivable from the axioms. So in this case, hoping that every theorem turns true, this is what we call consistency. So this is consistency. Or in this particular example, that would be inconsistent. If we ever came up with a theorem that was derived from the axioms that under interpretation became a false mathematical statement, we would say mathematics, or this formal system rather, is inconsistent. Or at least that's externally inconsistent. Internal inconsistency is different. Internal inconsistency is if you could derive both SS0 equals SS and also SS0 equals SS0. So this is under interpretation, 2 equals 2 and 2 equals 3. If you could somehow derive both of these strings from the axioms applying the rules, that would have an internal consistency. Whereas external consistency is if you, under interpretation, you come up with a false statement. Hoping that every single true statement, when written in the formal system, is derivable, this is completeness. So that means if it was the case that we could come up with some number statement, which is about natural numbers, that when we convert to a string that is within the system, and we say well-formed. So for example, earlier in the PQ system, dash dash P dash PP dash Q dash, that's not well-formed. There are two P's, and we know that just by inspection, two P's are impossible. So we say this is not a well-formed string. So completeness is for every single true statement about number theory or natural number theory. If we could write a well-formed string in the formal system, we would hope that that well-formed string could be derived from the axioms. Because if that string could not be derived from the axioms, then the formal system is incomplete. So the formal system is unable to create a derivation for a string that, under interpretation, comes out as a true statement. So now we have everything in place to finally go to Gödel numbering. What Gödel did is he found a way to make numbers isomorphic to symbol manipulation in the formal system. So let's write out a few of the symbols. We have this symbol. Let's say let's just have one as corresponding to this symbol. This symbol, by the way, means and. It's a logical statement. So true and true is equal to true. True and false is equal to false. False and true is equal to false. And false is equal to false. So if this particular statement is true, and you put the symbol and this also is true, then the whole statement is true. So and just says, is both the statement before me and after me, are they both true? If so, this whole statement is true. If either one of them or both of them is false, then this whole statement is false. So that's all that the and symbol means. It's just a logical operator. So with Gödel numbering, what you can do is every single sequence of symbols or every single string can be converted to an integer in a well-defined way. So this is the string. And then let's call this the Gödel number. So what we do is we take the list of primes. So the first prime is 2. We take 2 to the power of whatever the number of the first symbol is. So 2 to the power of 1 times 3 to the power of whatever the number of the second symbol is, 2, times 5 to the power of whatever the symbol of A is, which is 3, times 7 to the power of the colon, which is 4, times 11 to the power of the S, which is 5, times 13 to the power of A, which is 3, times 17 to the power of the equals, which is 6, times 19 to the power of the 0, which is 7. So this is some big number. Just call it x. Doesn't matter. It's not the point. If you have x, you will be able to go back to this symbol by doing a prime factorization. So what you do is you start with x, you divide it by 2, see how many times it divides by 2. Okay, it only divides once. So let's move on to 3. Divides by 3 twice. Okay, so we know it's 1, 2. How many times is divided by 5? 3 times? Okay, 3. So on, and then you get this list of numbers. 1, 2, 3, 4, 5, 3, 6, 7. You look at this, and then 1, 2, 3, 4, 5, 3, 6, 7. You write out all the symbols and you get back to the string. So here we are able, what the Gödel numbering does is it allows you to have a a number that corresponds exactly to the string. So any string we write in the formal system, there is a unique Gödel number. So that is the first step. The next step is to specify how the rules work. So for example, let's say there was a rule such that if you have SSS S0 equals A, you are allowed to rewrite that as SS0 plus SS0 equals A. So let's say this was a string in the formal system, or a theorem, let's say it was somehow derived. Then there is another rule in the formal system that allows you to rewrite it as this. Now remember, everything in the formal system is just blind symbol manipulation. Under interpretation, this rule is splitting up a number into, let's say, halves. So there is the strings, and then we're going to have the interpretation. So for the first one, we have this is the string, this is the Gödel number, and the interpretation of this is that natural numbers are positive. Or at least -1 is not a natural number. And then truth value, we could say this is true. So let's say we have, so that's just for a string. Now, so this is for, say, strings. So strings, we have some formal system string, we have a Gödel number that corresponds to that string, we have an interpretation of that string, and we have a truth value of that interpretation. So now we can have rules. So let's say this is one of the rules. If this is a string, then there is one of the typographical rules, typographical meaning the manipulation of physical symbols, that allows you to go from this to this. If there is an even number of S's, you can split it into 2 and 2. The Gödel number of this, well, it's not really the Gödel number, it's more like there's a function. So let's say that this particular thing is some integer x under the Gödel numbering. This string is, so yeah, this string has the Gödel number x, this string has the Gödel number y. So the equivalent is the function of x is equal to y. So there is some function that when you apply that function, and that function might be extremely complicated, involving lots of additions, multiplications, divisions, subtractions, whatever, there is some operation that you can apply to this integer x that results in this integer y, where this integer x is this string and this integer y is this string. And this is constructed in such a way that no matter what x is, as long as x is some string of this form, it results in y, where y is some string of this form. So x didn't have to be 4 here and 2 and 2. It could have been 6 s's and 3 and 3. Let's say there's something SSS 0 equals A, and there's the typographical rule allows you to write SSS 0 plus SSS 0 equals A. And let's call this, let's say the Gödel number of this. When I say the Gödel number of a string, I mean applying this process to a string. Let's say the Gödel number of this string is x1. The Gödel number of this string is y1. Then function of x1 is equal to y1. So this is some sort of arithmetic rule that is isomorphic to the typographic rule. So the interpretation of this is splitting an even number in 2. And the truth value, well, it's not really relevant. It's a rule. Talking about the truth value of a rule doesn't make all that much sense. Now I'm going to combine everything I just talked about into one. So let's call this the uncle. This is the uncle. It is not the case, the uncle string, that there exists a number such that there exists another number such that, I'll get to what PP means in a minute. So PP means proof pair. PP means A is the Gödel number of the derivation of A prime. A prime and A are integers. So A prime is an integer that corresponds to a particular string or a particular theorem. A is another integer which corresponds to every single line of the derivation, all put together Gödel numbered. So let's say we have the axiom 1 and we apply a rule to it, we get theorem 1, we apply another rule, we get theorem 2, we apply another rule, we get theorem 3. So in this case, A1, A2 T1, T2, T3. When you Gödel number this, you get A. And then T3, which is the final theorem you derived, is the Gödel number, has the Gödel number A prime. So that's what A and A prime mean. And PP means proof pair. So A is the proof of A prime. So that's the proof pair. So PP A prime means simply that A prime is the end of the derivation of A, where A and A prime are the integers of theorems. Under interpretation, this part just means A prime is a theorem, or rather the string that corresponds to the Gödel number A prime is a theorem. AMQ, arithmoquinification. This is what Hofstadter calls it. Arithmoquinification is when you have a string, where you have some string, a free variable, and some more string. You take the Gödel number of that and you sub it into its free variable. So a very simple example is there exists an A such that A is equal to A prime. So this string, let's look at this string. What is this string saying? There is an A such that A exists to A prime. So A is not a free variable because it's part of the statement about it saying there exists an A. A prime is a free variable. So if we arithmoquine this, what's that going to be? Well, the first thing we do is look at the Gödel number of this string. Let's call the Gödel number of this string W. W is the Gödel number of this string. What we do, we arithmoquine this. Well, it'll become the string E. There exists an E such that A is equal to W. We have subbed in the Gödel number of the string into its own free variable. That's what it would put. Although I've written it out in strings, but here it's in Gödel numbered. So A prime prime is an integer. A is an integer. Now you might be able to see where this is heading because A prime prime is a free variable. It's the only free variable. So what happens if we arithmoquinificate this? And this means A prime is the arithmoquinification of A prime prime. So this Gödel number is W. This, let's say the Gödel number of this is V. So what we can say is the arithmoquinification of W is V. So what this is saying, the arithmoquinification AMQWV, what this is saying is when you take the Gödel number W, you convert it to a string, and then you look at the free variable of that string and you sub in W into that free variable, and W, of course, isn't a symbol. It's actually SSSS, lots and lots and lots of SS's, zero. It's actually, so when I write W, I just mean a lot of S's, which correspond to the number W. That taking the Gödel number of the resulting string of the subbing in is V. So that's what this part does. So what happens when we arithmoquinificate this string? Let's say this had the Gödel number U, lowercase u. So let's do it. Let's write out the arithmoquinification. Now this is U there, comma, A prime. Now of course, again, that's not really U. It's more like SS U number of times 0. So that's really what should be in there, not U. But what is this saying? It is not the case, that is what this means, not. It is not the case there exists an A and A prime such that A forms a derivation of A prime and A prime is the result of the arithmoquinification of U. Okay, again, this is confusing. So it isn't the case that A prime is a theorem because this part is just saying A prime is a theorem. So it is not the case that A prime is a theorem and A prime is the result of the arithmoquinification of U. So what is the arithmoquinification of U? Well, that's what we just did. We just arithmoquinified U. So this statement itself, this is the arithmoquinification of U, which means the Gödel number of this number is A prime. But this statement says A prime is not derivable. So this statement is saying, I am not derivable. the reason why this works, and it's not just some random made up stuff, is that symbol manipulation is isomorphic to the Gödel numbers and the number manipulation. So we can create a little bit of a table. So we have the string, and this is just some string. And then we have the number manipulation, number. So we have some string, and this string is meaningless symbols. We have the number, which is some long number. We have the interpretation, which is the interpretation of the string. And we also have the truth value of the string. So this string, let's write this string. This string, let's put it in here, and let's call it G, string G. Now it has the number, let's call it lowercase g, or a prime equals g, same thing. The interpretation, this number does not have a certain property. So what this proof pair is kind of really doing is saying that G does not have a certain property. So for example, let's say evenness is a property. 10 has the property, 11 doesn't. In this particular case, when I say evenness, I mean using the rules of the formal system. So numbers and the manipulation of numbers are isomorphic to the strings and the manipulation of strings using this Gödel numbering. So this statement, when we interpret it as a string, or rather when we look at it as a string or we look at it as Gödel numbers, it's really the same thing. So the interpretation is G is not derivable. That's the sort of symbol or formal system interpretation. You could also say that the number G, or the Gödel number G, does not have the property of applying functions, let's say f, g, and h, to integers a, b, and c, where a, b, and c are the Gödel numbers of the axioms, and f, g, and h are the arithmetic processes that are isomorphic to the rules of the formal system. So to clarify, we have the formal system, we have axioms in the formal system, we also have rules in the formal system, we also have theorems, which are strings that are derived from the axioms using the rules. And then we have the Gödel numbering system. So the axioms are like, you can say, starting integers. And then the rules are functions that you can apply to those integers. And then the theorems are integers that have a certain property. So what G is saying is that G does not satisfy a certain numerical property. It's sort of like saying 10 is not equal to 20 divided by 3. A better example is 11 is not equal to 2 times a, where a is a natural number. So if a is a natural number, 11 does not satisfy the property of 2 times a. So 11 is not even. So in the same way, the G is saying G does not satisfy a certain numerical probability, which is isomorphic to saying that G, the string, is not a theorem. So now comes the problem, is this true or not? If the string is not derivable, then it is saying it's a truth. So either the string is not derivable, but it's saying, G is saying I am not derivable. So that means it's a truth, which means that there's a truth about it's saying a mathematical truth. Under interpretation, it's truth, but it's not derivable. When I say mathematical truth here, I mean it says G does not satisfy a certain numerical probability. Whereas on the other hand, if it is derivable, then it is false, because it's saying it's not derivable, so it must be false under interpretation. So if this were true, maths is incomplete, or the formal system is incomplete. And if this were true, then it would be inconsistent. Now, if we make the assumption that the system is consistent, because all of the rules, all of the axioms are the most basic truths. We can't see how the axioms are wrong. All of the rules are super basic. We can't see how the rules can be wrong. So there is no way that you could come to a false statement by manipulating the symbols according to the system. At least that is the assumption, which means that this formal system must be incomplete. So there are some truths about mathematical numbers that are not derivable using mathematics, or at least the formal system, which is isomorphic to arithmetic processes. So that concludes my understanding of it. I do not have a complete understanding of Gödel's incompleteness theorem. There are a lot more nuances and details that, one, I didn't go into, and two, I don't understand. This was just my understanding of it. But the key point here, and the key point that, well, at least I think Hofstadter is trying to make here, is that self-reference is what creates this. The ability of a system or something within a system to reference itself. And that's a key point. So let's say we have a thing, to be very literal here. We have a thing. Now, what if we have a meta thing, a thing that describes the thing? But what if that meta thing turned out to be the thing? So that's what we had in the case of the Gödel numbering. We had the formal system, or the number formal system, or just numbers more broadly. And we were able to make statements about the formal system, about numbers, using numbers. So for example, we have language. And then what we use to describe language is meta-language. But there is no meta-meta language. We can use meta-language to describe itself. So the idea here is that we create what Hofstadter calls a strange loop. It's where you move up or down on a hierarchy, and instead of going up or down, at some point you come back to the same level. And this is where Escher's work starts to come in. This idea of strange loops comes up in the work of Escher, and Hofstadter points this out. So for example, we have the artwork Print Gallery. In Print Gallery, we have a boy, or a man, he looks about early 20s, and he's looking at a painting. And if you follow this painting, it turns out that he's actually inside the painting. Normally, when you look at a painting, you would think that the painting is at a different level as the actual reality that you're standing in. So let's say you're in an art gallery, and that's one level, and then there is the world of each of the paintings. Those are all, you could say, lower level worlds. But in this particular piece of artwork, you move down a level into the painting, but you actually arrive at the same level that you started off in. This painting is the reality. So this is a strange loop. We've gone one direction in the hierarchy, and we've come back to the same point. Another example is drawing hands. With drawing hands, we have the top hand is drawing something. So normally in terms of levels, we would think that there is one level, which is the thing that's being drawn, the two-dimensional thing on the paper. And then at a higher level, we might say, we have the hand or the object that is doing the drawing. So if we look at the left half of the diagram, we have the low level, which is the collar of the shirt, and then on the drawing. Then we have the higher level, which is the hand doing the drawing. So let's follow the hand. The hand come around, the hand turns out to actually be part of another drawing. Okay, and then there's another hand, so we have to go up a level. But this second hand actually comes around to join the initial thing being drawn. So we've moved up 2 levels, but we've arrived back at the same level. So this is another kind of strange loop. Hofstadter calls it strange because it's unexpected and doesn't make sense. With hierarchies, you can go up, you can go down. But a strange loop happens when you go up or down, you actually arrive at the same level. Now this is actually a little bit different to infinite regress or recursion. For example, if you record a screen and you display what you're recording on the screen, you'll get an infinite regress. This is not a strange loop because you're moving down levels, but you're never actually coming back to the original. The lower levels are not exactly the same as the high levels. The lower levels are, you could say, lower resolution versions of the high level, but it's not actually the same thing. So while what you're seeing on the screen is the same as what you're seeing in real life, and each level below that, it seems to be the same, the phone or the screen or whatever, but it's not actually the same thing. It's just a lower level representation of it. So a strange loop is when you move across levels and you actually arrive at an original level, whether that's after 1 or 2 or after n number. That's the number of levels you have to move across to come back to the original is not really the point. The point is it's strange that you're moving in a direction, but you come back to where you started. Another example from Escher is ascending and descending. So here we have a staircase, and you start, let's say we start on the part of the staircase that's closest to us, the corner. Let's say you move up, so you move left up, and you're walking up the stairs, and then you keep walking up the stairs, and you somehow, despite the fact you're walking up, come back to where you started. Alternatively, we could walk down the stairs, and you keep walking down the stairs, and you somehow get back to where you started. So this is another kind of strange loop. You move in one direction, but you come back to where you started. So we have this hierarchy, and when this hierarchy loops back on itself, we call it a strange loop. We could also call this a heterarchy. So a heterarchy is a set of things, but it's not leveled as in a hierarchy. Hierarchies have levels. Heterarchies are things, but each of the things can be at multiple levels, perhaps at the same time. So you have one thing might be above one thing, but also simultaneously below the other thing. So it's sort of a loose or a tangled, or he calls it a tangled hierarchy. Another example of a heterarchy comes up in programming. So, for example, we have the function f. This function f, at some point inside it, it calls on the function m. So if we have a look at m, which we would think is moving perhaps down a level, because normally when you have, say, a function, within that function, perhaps it calls another function, that other function returns some value, and then the control of the program passes back to the original function. For example, here we have two functions. So we have the function, let's call it a higher level. It takes in a number, and then it squares that number. So this just means squares. And then what will happen at this point, lower level n, it calls a second function. So it pops down, and then it'll calculate this. In this case, if let's say n is 2, 2 equals 2 squared, so that'll be 4. It'll pass in 4 into this function. And so it'll return 4 plus 5. So a will equal 9, and then it will go 4 times 9, which is 36, and so it will return 36. So there's this idea of we move down levels, and then we move back up levels. But what happens in the case of functions that reference each other? Here we have two functions that reference each other. So here we have function f, but within function f, it is defined in terms of, at least in part, of function m. But if we have a look at function m, it is defined at least in part in function f. So the question is, which of these programs is at a higher level, or which of these functions is at a higher level than the other? In this case, it was pretty obvious which one was at a higher level. We started here, then we pushed into this function, and then we pushed into an even lower function, and then we popped back up to here, and then we popped back up to here. So it was pretty obvious that this is the lowest level function, and this is the medium level function, and this is the highest level function. But in this case, it's not so obvious. Perhaps this is the highest level function, the actual print function that we're calling in the first place, but then which of these two is a higher level? You might say f is at a higher level because it's the first thing we're being called, and in a sense that's true, but then it calls on m, but then the m calls on f as well. So it calls on each other. So this is a bit of a kind of a strange loop, where this references this, calls on this, and this calls on this. So neither of them is really above the other in the hierarchy. And following through the logic of this is, I'm not going to do it step by step, but we will go through it very quickly just to see what happens. So we start off here in the main module. So now we're going to go into this program. So now here you can see at the left, we're in the function f. So n we've put in 5, so this first case doesn't get executed, it goes straight to this case. So what happens here, it goes n is 5, so it has to find f4, so it has to go back into f. So you can see at the left, we've now pushed into to f, which is at a lower level. And then we do it again, and then again, and then again, but now n is 0, so now it's going to return 1. So you can see we're going to start coming up, but as soon as we come up now we go into m, because now that f of 0 has been defined, we now know what this is. It's 0, so is it 0? It's 1 or something. Oh yes, it's 1, because it returns 1, so now it has to look for m of 1. So now it goes to this function, and then it has to check, and then it has to call on itself again, it returns 0. But then now it has to go on f. So you can see at the left it's starting to get a little bit complicated. We're 1, 2, 3, 4, 5, 6, 7 layers down, and you'll see it gets a little bit more complicated. So if we just keep going through, it's going to keep going back and forth, and you can see sometimes the stack gets shorter, sometimes it gets longer. This is the stack, you can say. So this is a bit of a strange loop, because we've got one is not clearly above the other. There are points where m is above f, f is above m. Neither of them are really at a higher level than the other, because they're defined in terms of each other. So here you can see fm, fm. So f is above m, but m is above f, f is above m, and so on. And we're back. So now we finally returned it, and then it prints out the value 3. Yet another kind of strange loop in programming are quines. I briefly mentioned these a little bit earlier in the context of words, but they can be applied very neatly in the context of computer programming. Here we have 3 quines. So what happens when we run this program? If we have a look at the output, this is actually exactly the same as this. So the output is the same as the input. So if we just copy the output, you'll see that it returns exactly the same thing. So we could just, if we wanted to, keep doing this, and it would just keep returning exactly the same thing every single time. These are 3 separate quines, by the way. So if I get rid of, say, this and this one, then this line will print itself. So you can see here, it's printing itself. What this touches on is the idea of subject and object. So the idea is we have the subject, and perhaps the subject is the one doing the thinking or doing the calculating or doing something, and the object is the object of that thinking or the object of that calculation or something. So what happens in this particular strange loop is that the subject and the object are the same thing. So we have in this case, with the programming, we have the subject, which is the actual program itself, and then the object, which is, you could say, the output of the program, but they are actually the same thing. Another example of this is the human mind. So this is one of the key ideas in Hofstadter's book, which is that the human mind is a strange loop, and he explores this much further and in much more detail in his second book, I Am a Strange Loop. But the idea is that human minds are both the subject and the object of their own thinking. So for example, you can think, and you can think about things, but you can also think about yourself thinking. So the subject of thinking and the object of thinking can be the same thing. So with the meta-language and the language example, you've got the language, you've got the meta-language, but then the meta-language is sufficiently powerful to talk about itself. So for example, you have the low-level neurons, and the neurons in your mind build up to these higher-level concepts and symbols in your own mind, and those symbols at the highest level in your own mind, the conscious level, they are sufficiently powerful for them to begin representing themselves and start thinking about themselves. Also, with the Gödel numbering of formal systems, the formal system in mathematics is sufficiently powerful for it to contain the description of itself. So by using Gödel numbering, or the isomorphism between formal systems and arithmetics with integers, the integers are able to describe themselves in some way. The formal system contains its own meta-language through the Gödel numbering. Throughout the book, Hofstadter creates this very interesting analogy, or you could say isomorphism, between Gödel numbering, the mind, computer systems, and also genetics, because he talks a fair bit about genetics and DNA, and how DNA contains information about itself. But this part I didn't fully understand. My background in genetics and biology is limited compared to my background in mathematics, so I can't really explain this in good faith. However, that this link between all of these different areas and the idea of self-reference actually was quite interesting. And now that I've read about it and understood it, it seems to be quite a fundamental part of intelligence, I suppose. And that's part of his thesis, is that a core part of intelligence is the ability to self-reference. So when an entity or a system becomes sufficiently powerful enough to reference itself, it starts to become a new type of entity. It reaches a kind of a level or a space of operation that's qualitatively different to entities or systems that do not contain the machinery of their own self-reference. That's all I'm going to talk about the book for today, but I would say that for anyone interested in theoretical computer science, genetics, pure mathematics, this book is a must read. If you're considering going into this field, if the stuff in this video is interesting to you, definitely read the book. The book goes into a lot more technical detail than I've talked about here. What I've talked about is barely just broad brush strokes of the actual nuance and complexity of the book. Every page, almost every single page of the book was a mission. Some of the pages I had to spend 20-30 minutes on to get through, especially the part about the Gödel, the final crux of the Gödel string working. I had to sit with that for a good hour just for it to finally make some kind of sense. So it's a very dense book, but I found extremely worth it. And if the stuff in this video seems interesting, then I would highly recommend going through and reading the book. But if not, I hope you've enjoyed the video, and I will see you all next time.